In this segment, we want to look at the definition of the definite integral, starting with the following example. Suppose you drive 30 miles an hour for 2 hours, then 40 miles an hour for an hour and a half, and finally 20 miles an hour for 4 hours. We'd like to do two things. We'd like to calculate how far you traveled in the 7.5 hours, and then we'd like to look at a graph of velocity versus time. The calculation of distance traveled is fairly straightforward. You know that distance is rate times time. So the distance traveled will be 30 miles an hour times the first 2 hours, plus 40 miles an hour times the next hour and a half, plus 20 miles an hour times the final 4 hours. And if you do the arithmetic, that adds up to a total of 200 miles. For the graph, if we look to the left here, we've got time on the horizontal axis measured in hours, and velocity along the vertical axis measured in miles per hour. And you can see that over the first 2 hours we've got a velocity of 30, and then for the next hour and a half it jumps up to 40, and then for the final 4 hours, from 3.5 to 7.5, it drops down to 20. But if you look at the calculation of distance, for example, in the first segment you've got 30 times 2. Well, 30 is the height of the graph, and 30 times 2 is actually the area of this rectangle under the graph. And the same is true for the other two segments of the velocity graph. So in fact, the total area under that graph is the distance you traveled. And so that's the key observation that we want to make in this example, that the distance traveled is actually a sum of rectangle areas equal to the area under the velocity graph. Now imagine a car accelerating up to cruising speed so that its velocity is always changing. For example, suppose that the velocity can be represented by the function t squared over the time interval from 0 to 8, where velocity v is measured in feet per second and time is measured in seconds. How far does the car travel over this time interval? We can't use the distance equals rate times time formula directly because the rate, that is the velocity, is never constant over any interval of time. It's always changing. We can, however, use rectangle areas, only this time we'll use them to approximate the distance. The graph shows the velocity function t squared over the time interval from 0 to 8. We're going to start our first approximation by breaking the time interval up into two pieces, each of width 4. We're then going to construct a rectangle over each subinterval. The width of each rectangle will be denoted by delta t, which is 4, and the height of each rectangle will be determined by the value of the function at the right endpoint of each subinterval. So the height of this first rectangle is the value of the function v of 4, and the height of the second rectangle is the value of the function v of 8. So for this reason, these rectangles are referred to as right rectangles. The height of each rectangle represents a velocity, and the width is an interval of time. So the area of each rectangle represents a distance, just as it did in our earlier example. So if we look at this first rectangle, does it represent the distance the car travels over the first 4 seconds? Well, unlike the first example, the answer is no, because we weren't traveling at this velocity for the entire 4 seconds. Most of the time, we were actually going more slowly. So the area of this rectangle is actually greater than the distance the car travels over the first 4 seconds. And similarly, the area of this rectangle would be greater than the distance traveled over the second half of the interval. So if we add those two things together, we'll get an upper bound on the distance the car travels over the whole 8 seconds. So let's figure out what the area of those two rectangles actually is. Well, the area of the first rectangle is its height, v of 4 times delta t, and that's over here. And the area of the second rectangle is its height, v of 8, times its width, delta t. Well, we know that v of 4 is 4 squared, v of 8 is 8 squared, and if we do the arithmetic, we find out that the total area of those two rectangles is 320 feet, and so we know, in fact, that the car must have traveled less than 320 feet over the whole 8 seconds. Okay. Well, now let's look at what happens if we look at left rectangles. So now we're going to, again, have the interval divided up into two pieces, but now we'll build our rectangles by choosing heights determined by the value of the function at the left-hand endpoint of each interval. So the height of the first rectangle will be v of 0, which is 0 squared or 0. So this first rectangle happens to have a height of 0. And the height of the second rectangle is v of 4. Okay. And similarly to the right rectangle situation, each of these rectangles represents a distance, but now this distance has to be less than the car traveled over that interval, because in fact most of the time we were traveling more quickly than v of 4. So if we add up the area of these two rectangles, we'll get a lower bound on the distance the car travels. Well, the area of the first rectangle is its height, v of 0, times its width, delta t. And similarly, the area of the second rectangle is v of 4, its height, times its width, delta t. V of 0 is 0 squared, v of 4 is 4 squared. If we do the arithmetic, we get a total of 64 feet. And that's a lower bound on the distance traveled. If we put these two things together, we can see that the total distance the car traveled must be somewhere between 64 feet and 320 feet. Now obviously that's not a very good approximation, so the question is, how do we make it better? And we make it better by making delta t smaller and using more rectangles. So I'm going to temporarily switch that off, and I'm going to take n equals 2 and move it up to n equals 4. So that now looks like this. So the sum of these four rectangles will be an upper bound on the distance traveled. And if we look at the arithmetic now, the height of the first rectangle is now v of 2, because that's the right-hand endpoint of this smaller interval now. And the right-hand endpoint of the second interval is v of 4, and so forth. So the formula for the areas of these rectangles would be the height of the first one times its width, height of the second one times its width, and so forth. And again, we know the value of the function at these four places, and if we do the arithmetic, we now find the total area of those four rectangles is 240 feet. And that's a better estimate for an upper bound, a better upper bound for the distance traveled. And if we look at the left sum, that's going to look like that. And the height of the first rectangle is v of 0. The height of the second rectangle is now determined by the left-hand endpoint, which is v of 2. And if we move over to here, the height of this rectangle is v of 4, v4 being the left-hand endpoint of this interval, and so forth. And if we calculate all the areas, height times width, height times width, height times width, we get an area of 112 feet. And if we put those two things together, we can see that the distance traveled now has to be between 112 and 240, and that's a better estimate than we got when delta t was 4. So now, obviously, that we want to keep increasing the value of n, the number of rectangles, and decreasing the width, delta t. So let's see what it looks like if we were to take this and, say, move it up to, say, n equals 20. Right there. We can see that the left sum and the right sum have now moved closer and closer to each other, and you can get a sense of that in the picture too. The sum of the blue rectangles and the sum of the red rectangles are now sort of closer to each other, and we now have our distance traveled trapped between two numbers that are closer than they were before. So now let's fast forward and take n, and let's say we stop right there for a second. You can see that the left sum and right sum have drawn even closer to each other, and you can sort of see that in the picture as well. And if I take this out all the way out to the end, and if we actually did all the calculations, we would see that the distance now is between two numbers that are very close to each other, giving a very good approximation of the actual distance traveled. So here's the conclusion that we'd like to make based on this example. As delta t, the width of the rectangles, gets smaller and smaller, the left and right rectangle sums approach a common value which represents the distance traveled. This common value is called the definite integral of the velocity and is denoted by this set of symbols. In addition, as in our earlier example, the distance traveled is actually equal to the area under the velocity graph. You can see that in the picture, that as we take more and more rectangles, we get closer and closer to the actual area under the curve t squared. But that area now is a limit of sums of rectangle areas. So here's the formal definition of the definite integral. We start with a continuous function defined on an interval. We're going to divide that interval up into n equal pieces, and when we do that, each piece will have a width denoted by delta x, which will be b minus a, right minus left, over the number of pieces. In each subinterval, pick a point xi and form this sum, height times width, height times width. This is the sum of the rectangle areas. Then take the limit of these sums as delta x goes to 0. The result is a number and is called the definite integral of f from a to b. Some important notes about the definition. The definite integral is always a number. A is called the lower limit, b is called the upper limit, f is called the integrand. And the sum is called a Riemann sum. And the final note is that the points xi can actually be chosen in any way as long as each one is in exactly one subinterval. The most common choices are left, right, which are the ones we use in our example, but the midpoint of each subinterval is also a choice, and we'll look at that in some of the examples later on.